Okay, so today we're going to talk about the integral test. This is something you would use on a series where you think it's pretty easy to integrate the series, and it's not already an easy series like a p-series or a geometric series, something that we already know how to do. So first, let's look at an example over here on the right. I'm going to draw an example of a series. So let's say it's a series where the sequence, that if we graph the sequence, an, that, let's say it's 1, and then 1/2, and then 1/3, and then 1/4, and then 1/5, and then 1/6, and it continues, ... getting closer and closer and closer to the x-axis. So the series would mean adding up all of these values generated by this sequence. And what we're going to notice here, what the integral test says, is that if you think of the function that runs through these points, so remember that the values in a series are going to be adding up fixed values, so it's not a function itself. But we could talk about the function that runs through those, and we're going to call that f of x. So this green function here would be f of x that runs through those. So that's what this part here is talking about. If you think about that function, and what we're going to do is we're going to compare adding up the series to the area underneath the function that runs through those points. And what the integral test says is if you have an improper integral from 1 to infinity, the area under this curve, if this improper integral converges or diverges, then the series will also converge or diverge, which makes a lot of sense. If the area is getting small enough to converge, then the values themselves, when you add them up, these values that we would have, that when we would add them up to make the series, that those would converge. But if the area is getting too big, then the values would get too big. And so that's the idea behind the integral test. But there are three important checks that you have to do with the integral test. Check. One, you have to make sure this function that you're talking about, that this series is positive, it's continuous, and it's decreasing. So it's really the function that we're testing that goes through these points, because the series itself is a bunch of fixed values. And this only has to be true at some point beyond. So maybe the function isn't continuous and positive from 1 to 2, but then starting at 3 and beyond, it's continuous and positive from here on, then that's fine. This still applies. So this is what this part here, so this is at some point. We don't really care what happens with the first couple terms when we're adding it up, but from some point on, so like if you start at 1 and go to infinity, let's say the continuous decreasing and positive thing doesn't happen until 5, that's fine. We'll go from 5 to infinity. If that converges, then add a couple more terms at the beginning, and it will still converge or diverge. So when you're doing the integral test, in order to apply it, you want to look for something that you know how to integrate, and then you have to check to make sure it's positive, continuous, and decreasing. And these are things that you can check pretty quickly for the most part. The decreasing is the hard part. And on the AP Calculus exam, most of the time, students are not required to prove the 3 conditions, but you definitely have to state them. Okay, so most of the time you'll be able to get the first 2 just by looking at it. So, for example, here we're talking about f of x being this function x over x squared plus 1. Or if you want to, that's the function. You can use x's. You'll see a lot of people do that. But if you want to just call it f of n, you could just call it f of n. It's just a variable. But if it gets confusing to you, you can call it x. And then we need to first see if this is continuous for some value bigger than 1 to infinity. Or let's do positive first, actually. Let's do positive first. So positive for some value bigger than 1. Well, this denominator will always be positive because it's being squared. And as long as we're going from 1 to infinity, this guy will be positive as well in the top here. So we definitely know that f is positive for n greater than or equal to 1. That's where we're starting. And then for continuous, I usually just look at, do we know any places where this is not continuous? Well, that would only be when the denominator is equal to 0, and this denominator won't be equal to 0 because of the square. So f is definitely continuous on n greater than or equal to 1. So these two you'll definitely usually be able to just visualize, see, check, and then just say that it's true. Now, decreasing sometimes is a little less obvious. So here I'll show you a way that you can check for decreasing. Remember that something's decreasing when the derivative is negative. So what we can do is we can take the derivative. So here that will be low. We'll have to use the quotient rule. So low d high minus high d low all over the square of what's below. And then if we simplify this in the top, we'll get n squared plus 1 minus 2n squared all over n squared plus 1 squared. And this will become n squared minus 2n squared will be 1 minus n squared over n squared plus 1 squared. And in order for something to be decreasing, we need to know when this is going to be less than 0, right? When the derivative is less than or 0 to see when a function is decreasing. And this bottom part here will always be positive because it's being squared, but this top part here will be negative as soon as n squared is bigger than 1, because subtract that from 1 and you're bigger. So this is definitely going to be less than 0 for n greater than or equal to 1, because, or I guess it's less than or equal to 0. So we'll just say greater than 1, because it just has to happen at some point bigger than that. Okay, so f will be increasing or decreasing for n greater than 1. Okay, so we've checked each of those three things, and so then in order to apply the integral test, what we need to do is we need to figure out, does this integral from 1 to infinity, this improper integral, converge or diverge? And if it converges, then the series converges. If it diverges, then the series diverges. So that's what we're checking now. Again, if you want to switch to x's, you can switch to x's. All right, so this will be a pretty easy u sub for finding the antiderivative here. If we use u equal to n squared plus 1 and du equal to 2 dn, divide by 1/2. So then we'll end up with 1/2 du over u. So this is going to just be 1/2 ln of n squared plus 1. And then we'll evaluate that from 1 to infinity. I probably shouldn't write it that way. We should plug in our b. So we'll do the limit as b approaches infinity of 1/2 ln of n squared plus 1, evaluated from 1 to b. So then we will plug in b, plug in 1, subtract, and then take our limit. So we'll have 1/2 ln of b squared plus 1 minus 1/2 ln of 1 squared plus 1, so that'll be 2. And as we go to infinity, natural logarithm looks like this, right? So as we go to infinity inside, as this becomes larger inside, this will go to infinity. So this limit will be equal to infinity. And that limit does not exist. So that means that the improper integral diverges, which means that the series diverges. Okay, so let's look at another example. So for this example, first we'll check the three things. So one, let's talk about f of n being equal to n over the square root of 2n minus 5. So we can check to see if f is continuous, positive first. So this guy down here will only be defined when n is bigger than 3, because you would have a negative under the radical. So that's why this series starts at 3. And whenever we have something bigger than 3, this will be 6 down here minus 5. So as long as we're bigger than 3, this part under the radical will be positive, plus the radical will always be positive. And then as long as we're bigger than 3, then the top will be positive as well, because we're bigger than 3. So f is definitely positive for n greater than or equal to 3. Is it continuous? Well, the only place where it will not be continuous is when 2n minus 5 is equal to 0. And that will be when n is equal to 5 halves, which is 2.5. So as long as that bottom is not 2.5, then we'll be continuous. So f is continuous for n greater than or equal to 3. And you don't have to write this part down if you don't want to. I'm just explaining. Okay, so then we need to check decreasing. So let's go ahead and look at the derivative again to make sure that it is decreasing. So we'll look at f prime of n. We'll do low d high minus high d low. This will be 1 over 2 square root of 2n minus 5 times the derivative of the inside, which will be 2. So these 2's will go ahead and cancel out. And then we'll have that all over the square root of 2n minus 5 squared. So then we will want to simplify this to be able to see what's happening. I don't like this denominator right here, so let's go ahead and multiply top and bottom by the square root of 2n minus 5. Multiply this guy by the square root of 2n minus 5, and you'll just have 2n minus 5. And then multiply this guy by the square root of 2n minus 5, and that will go away. And you'll just be left with n. And then the bottom will have square root of 2n minus 5 cubed. So we multiplied this whole top by the square root of 2n minus 5 and the bottom by square root of 2n minus 5. And so then we'll end up with just n minus 5 over the square root of 2n minus 5 cubed. Now, we're looking to see if this is less than 0, right? Because for decreasing, we want the derivative to be less than 0. And the bottom will be positive as long as we're bigger than 3. Same thing as we said before. So the bottom will always be positive. And the top here will be negative when like n is equal to 3. But as soon as n is greater than or equal to 5, this is actually going to be positive, right? Because plug in 6, you're going to get a positive number. 7, you're going to get a positive number. So this is actually going to be greater than or equal to 0 when n is greater than or equal to 5. So this guy is decreasing up until 5, but after 5, it's not decreasing. So f is positive and continuous for n greater than or equal to 3, but f is decreasing. I'm sorry, f is not decreasing for n greater than or equal to 5. So we cannot use the integral test. At the moment, we don't really have something we can do with this guy, but we'll get a test to be able to test if this converges or diverges. But this is a good example for why you do really have to check these 3 things, because you can only apply the integral test when that happens. Okay, so let's do one more example here. We'll confirm whether the integral test can be applied, then use the integral test to determine convergence or divergence. So we'll start with checking out f, and we will look at 1 over n squared plus 1. We'll check to see if it's positive, which denominator here will be positive because of the square. Top is just 1, so f is definitely positive. We're looking at n greater than or equal to 1. It's going to be continuous as well because there are no discontinuities there. That denominator will never be 0, so f is continuous for n greater than or equal to 1. And so now we just need to check decreasing. So let's look at f prime. And we'll do low, d high, minus high, d low, all over the square of what's below. And so we'll have negative 2n over n squared plus 1 squared. And this guy, the bottom is positive, right? Always because of the square. And the top will be negative for any positive number in there. So this is definitely less than 0 for n greater than or equal to 1. So f is decreasing for n greater than or equal to 1. Okay, so we have checked our 3 things, and so now we can apply the integral test. So to do that, we will look at the improper integral from 1 to infinity of 1 over n squared plus 1. First, we will integrate. This is a special integral for us. This is arctangent. So then we'll do our better notation this time. Put in a b here first. And we will do arctangent of n evaluated from 1 to b, and we'll do the limit as b approaches infinity of this. So we'll plug in b. Plug in 1 and subtract. As we have said before, with the graph of arctangent, remember it's just tangent on its side. So these asymptotes here that are usually vertical for tangent are pi over 2 and negative pi over 2. So as we go to positive infinity, arctangent approaches pi over 2. So as b goes to positive infinity, arctangent approaches pi over 2. So this will be pi over 2. And then arctangent of 1 will be pi over 4, because that's where on the unit circle, sine and cosine are the same value. So we're looking at what angle is tangent 1. So that's going to be at pi over 4. And pi over 2 minus pi over 4 is pi over 4. So our improper integral converges because that limit exists, which means that our series, based off of the same idea, converges. Now, one thing that is important is that this series here, one thing we cannot say is that this guy equals pi over 4. This is not okay. The improper integral does. The area under that curve equals pi over 4. But nowhere did the theorem say that the sum will have the same value, right? You're adding up individual values now, not the area under the curve. So that's a very different concept. But if this guy converges, then this guy converges. So the integral test does not give us the sum of the series. It just gives us the whether it converges or diverges. So no, if I asked you find the sum of a series, so far the only one that we can really do that with is the geometric series. We don't know how to find the sum of a p series. We don't know how to find the sum of an integral series. So the only one we know how to do that with is geometric. We just know a lot of how to figure out if it converges or diverges.